calculus friends. Happy Thanksgiving, everybody. Hopefully you've been having a good weekend. I know it's already Saturday, and this is a little later than I had planned, but I've been having a good weekend too. But here we are talking about some calculus, getting ready to do our last lesson in this unit, which is to talk about the concept of total change and how it affects or how it relates to particle motion. Now, quite often we are going to be looking at functions that are rates of change. Okay, so we're going to have a rate of change function. And let's say f of x is a rate of change function. If I integrate a rate of change from a to b, that will tell me the total change from a to b. Okay. So if I have how quickly something is changing and I want to know how much it changed, integrating the rate from time between 2 points in time will give me an accumulation or a total change. Now, in particle motion, the rate of change that we're going to be talking about specifically is velocity. Okay. When we integrate a velocity function over an interval of time, we're going to get what's called displacement, or total change in position. So the change in position from A to B we can get by integrating a velocity function over an interval of time. Now, the two different things that you're going to be doing here, we may be asked to find displacement or total change in position, or we might be asked to calculate total distance, which is slightly different than displacement. Okay, and if we were in the classroom, I would stand up and illustrate this, but I'll just use my little stick person here. Okay, so there's my stick person. If my stick person walks 3 feet and then 2.5 feet back in the opposite direction, we would say his displacement is half of a foot from where he started. So if this is the start, if we do start plus 3 and then minus 2.5, then we're going to equal wherever we were at the start with a positive plus 5. Okay. However, if I want to talk about the distance that he traveled, I will count the 3 feet and the 2.5 feet all positive. So how far did he travel? He traveled a total of 5.5 feet, because all we're doing in distance is adding up the accumulation of the movement, versus in displacement, we're looking at what the result of the movement is. So it's the difference between taking the direction into account and not. Mathematically, that's velocity integrated versus speed being integrated. And speed being the absolute value of velocity, we'll look at how we're going to deal with that with the computer or with the calculator and without. We can also do this since acceleration and velocity have a similar relationship as velocity and position. If I want to find a change in velocity, I can do that with an acceleration integration. Okay. So change in position or displacement. change in velocity, total distance. Watch for the words total distance, because a total distance problem is different than a displacement problem, and we have to treat them differently. Okay, so the first thing we're going to do is we're going to calculate a displacement, or estimate, excuse me. I don't know. Oh, I'm sorry. We're going to estimate a displacement, and we're going to estimate a total distance. Since both of these are things we can calculate through integration, we can use the Riemann process or a trapezoid process to estimate. So in part A, given this table, we're going to use from 0 seconds to 30 seconds. We're going to integrate the velocity function, but we're going to calculate that through an estimation. This is a good time for us to review, and the reason this problem is in here is for us to review doing a midpoint Riemann. Now, just to make this a little clearer, if I ask you to do 5 rectangles, all of the same width, it makes sense, since we're going from 30 to 0, divided by 5 rectangles, 6-second intervals. So 0 to 6, 6 to 12, 12 to 18, 18 to 24, 24 to 30. Now, the height of the rectangle is in the middle of the interval. So it's going to be the 5, the 2, the 0, the -4, and the 0. If you want to draw this out for yourself, you can. It's going to look a little weird. But what you have to remember is when we're doing a midpoint, we pull the height, what's going to be the height of the rectangle, out of the middle value. So I'm going to need a 6 times -5, and I'm going to need a 6 times 2, and I'm going to need a 6 times 0, and I'm going to need a 6 times -4, and I'm going to need a 6 times 0. And once we put all that together, that's coming out to be -42 feet, which means at the 30-second point, we're at -42 feet from the starting point, or 42 feet to the left of the starting point. Now, I'm always going to be running through these problems quickly on a video because I know you can stop, you can rewind, you can replay, so I don't feel the need to slow down. You take it on yourself to slow me down as much as you need, or fast forward. Trapezoid method. Let me just kind of draw the first little pieces of data here. So we have a -10, a -5, a 0, a 2, a 4, and then a 0. All right. And that's at 3, 6, 9, 12, 15. That's me just pulling the data right from the table. So if I get to do 5 trapezoids, I'm going to use the same intervals, but they're going to create trapezoids. Now it's kind of weird. This first one's going to be a triangle because that base of the trapezoid is going to be a 0. The second one's also going to be a triangle. Let's see what the third one will be. Oh, this one's kind of weird. Yeah, this is not the greatest. Oh, but, oh, I totally messed up. Let's go back. Why is that all wrong? We want to calculate a total distance. Everything has to count as positives. we want to estimate what this would be if we integrated the speed function. So if I go to this table and I look at speed values, 2, 4, 0, 7, 4, 10, 0, 6, and I start making a graph, I'm going to be a 10, a 5, a 0, a 2, a 4, a 0, a 7, a 4, a 10, a 0, a 6. And so 0 to 6, that's my first trapezoid. Because this is, I'm sorry, this is when x is 0, when x is, I should put that underneath. Oh, okay, so x is 0, 3, 6, 9, 12, 15, 18. So really, this is the first one that's going to kind of look like a trapezoid. Because the 0 to 6 and then the 6 to 12 both have a 0 to 6, 6 to 12 both have the 0 as one of the bases. But then the 12 to 18 will have the bases of 4 and 7. And then 7 to 10, and then 10 to 6. So if you need to draw it in for yourself, sometimes that might not be a bad idea. Depends on how much data and what you need to understand it. But you can see how easy it is to get careless and forget that you're doing total distance. And when you do total distance, you're integrating the speed function or the absolute value of velocity. So all your outputs are non-negative. You either have 0 values or positive values. I'm not going to write out the full calculation on this, but I will tell you the final answer is 174 feet. And if you need more information to see the calculation on how I got that, working through my 1, 2, 3, 4, 5 trapezoids, I'll be happy to do that. So, both of these show how we would do this with a table. Okay? And typically, if we have a table of data, we're most likely doing an estimation problem, a Riemann sum kind of problem. But we still have to pay attention to the data we're given. Are we being asked to do a displacement where we're going to use the velocity values as signed values? Or are we going to be doing a total distance where we'll be using speed values? Okay. Problem number 2. Presentation, this time graphical. Velocity graph. Okay. The first few questions on here are review. Okay. I'm going to go through these pretty quickly. So if you want to fast forward or just do these and then check, or stop this and then do this and then check answers. When does the spider change direction at 6 and 9 minutes? Okay, how do we know that that happens then? The velocity changes sign. What's the acceleration at 2 minutes? At 2 minutes, we're right here. The acceleration would be 0. The acceleration is going to be represented by the slope on the velocity graph. So at 2, the slope of that section is 0. At 5, the slope of that section, here's 5, is -1. And if I throw some units on here, these are going to be inches per minute squared. inches per minute squared. The acceleration is undefined when the derivative of the velocity is undefined, and that's going to be at any corners or sharp points or cusps or turns. So how about t equals 3 is a pretty obvious one. T equals 8. But the other one that's kind of subtle is t equals 9. Acceleration is undefined there because you cannot measure an official slope at that transition. Like, what is the slope right here? Is it a 0 or is it the slope of that segment? What is your slope right here? Is it the slope of this segment or is it the slope of that segment? What's the slope right here? Is it this or is it that? Velocity is increasing. Velocity is increasing anytime my acceleration is positive. So in this function, this graph, that's from 8 to 9, and then from 9 to 10. I want to split that up because I'm technically, my acceleration's undefined at 9. When is the speed increasing? The speed is going to be increasing when the velocity and the acceleration have the same sign. And so how about from 6 to 8? My velocity is negative and my acceleration is negative. And then 9 to 10. Velocity and acceleration both positive. That's all unit 2. Okay. But you can see kind of when we start doing particle motion, we're just kind of doing particle motion. So anything out of unit 2 as far as particle motion goes, fair game in here in unit 3 as well. Now, G is easier than F. G says total distance. So total distance, we're going to integrate from 0 to 10, the absolute value of the velocity function. And so graphically, that means I'm going to, in this case, since I'm going to calculate this integral through actual geometry of areas, all my areas are going to count as positive. So if I look at this, the way I tend to look at this is I see a positive square there, and then I see that, and then this triangle is going to count as positive, and this triangle is going to count as positive also. All positive because of us doing total distance. So we've got a little 9 here, and then this triangle is 4.5. This triangle is 3. That triangle is 3. So in total distance, that's going to be 19.5 inches. Part F is a final position question. So if I want a final position, I've got to combine two things. Back to the beginning here. I've got to combine a displacement over an interval with a starting point. The starting point doesn't have to be at time 0. It can be at whatever time, as long as from that time to what your special ending time is, you can calculate displacement. So some kind of starting point, and then displacement over the interval of time will give you a final position calculation. So the most common thing to forget here is to forget about the starting position. Most of you will look at this and go, okay, this is, where am I? Oh, 10, I'm sorry. So I'm going to integrate from 0 to 10, the velocity, and that's going to give me the displacement. But I have to add on where we were at t equals 0. So if I want to know where I am at 10, I have to know somewhere where I was to start. and then how much I changed between that start point and the end, which in this case is 10. A good way to tell that you're being asked for a final position question is you're given a single interval, or a single time versus an interval of time. Something like this, it's going to say total distance. So that makes it a lot more obvious. You just have to be careful about pulling all the positive parts in there. Now, when I do part F, this 3 is going to count negative. Because if I'm going from here to here forward, everything above the x-axis is positive, everything below is negative. So I'll start at the 18. You're like, well, how does she know we start at the 18? It's because it's up here. It's always going to be up there in the problem somewhere if they want you to use it. They're going to have to give it to you. So you just got to go looking for it. You probably read right over it. So we're going to take that 18 and we're going to add on the result of this integral, which with positives and negatives involved is 13.5. And so the total value here is 31.5 inches. Okay, so that's about 20 minutes in. We have looked at how to do one of these problems, some of these problems if we're going to do a Riemann, how to do some of these problems if we're going to have a graph. Now let's look at some potential options for if we have an equation given for the velocity. I'm actually going to skip problem 3. This will be a good one for you to go back to. And I'm going to skip up to problem 4. And we're going to look at problem 4. So in problem 4, we now have an equation, an analytical approach to the velocity, not a table of data, not a graph to represent the velocity, but an equation to represent the velocity. And so if we're asked to do displacement from 1 to 4, this is going to be a fundamental theorem problem. This is me integrating from 1 to 4 that integral. Now, like I keep talking about, sometimes, if we may be looking at doing some things without calculators, or having to show your steps with fundamental theorem like you had to do on your quiz. So something like this, if you're going to show me fundamental theorem work, I'm going to need to see your antiderivative and the fact that we're going to evaluate it from 1 to 4. And I'm not going to do all the arithmetic right now because that's going to take up video time. But I will tell you that the answer you should get for that is negative 4.5 meters. Now, let's skip down to question C. The difference between question C and question A is I need to do question C like this. Now, to do this by hand is a big pain. And we're not going to spend any time quizzing you or testing you on doing a problem like this by hand. Okay? But what I want you to be aware of is what it would take in order to do this, in order to integrate the absolute value of the velocity function. Okay? Basically, and this is partially why part B is here, in order to do this correctly, I need to get a good picture. I need to think about the velocity function. And I need to think about the particle changing direction, which you start off by finding by thinking about when your velocity equals 0. So let's take a look at that for a minute. T squared minus t minus 6 equal to 0. Now, if you don't mess this up, like I did when I was first working it out, you factor it correctly and you get t equals 3 and t equals -2 as places where the velocity equals 0. You know, t equals -2, not really relevant because we're not talking about negative time. We rarely would talk about negative times, but specifically in this problem, we're talking about the times between 1 and 4. So what does that mean? That means that T3, my velocity changes either from positive to negative or negative to positive. Let's see. Here's 0. If I go back to my velocity function right here, if I put like a 1 into that velocity function, I'd get a negative. But if I put something bigger than a 3, like a 4 in, I'd get a positive. So my velocity curve must be coming up like that. Now, here's what that means. If we talk about the part from 1 to 4, I need to know that this is essentially a negative area, and this is essentially a positive area, so that when I do this problem, I can say, all right, I'll do the part from 1 to 3 of the velocity, but I know that's going to come out to be negative, so I'm going to make it be its opposite, so it'll be positive. And then, because this is 3 right here, and then I'm going to do 3 to 4, and it's already positive. Let me say that again. When we were doing total distance, we have to do the absolute value of the velocity. So I need to know when the velocity function is going to create a negative area in this interval, if at all, so that I can count that part as positive and then count any positive parts as positive. Just exactly what we did back here. We could see this guy was negative, but when we did the total distance, we just counted him positive. Seeing the velocity graph is a lot easier. When you don't see it, you have to sort of figure out what it's going to do, or you have to, you know, you may not have a calculator. And if you do have a calculator, we are not going to do any of that nonsense, because we're going to do exactly this. Watch. Something cool. Okay. All right, here we go. Big secret of your calculator. Number 1, math 9. You can do integrals. You can do definite integrals on your calculator. Most of you already probably knew that. And you're like, what did she do that again? She did, oops, math 9. Now, if you are not getting that, it might be because you don't have an 84 plus, or it might be because you have an 84 plus that's not updated. An 84 plus or better is really what you need to be able to do this. You can do it on the 83. It's just not very pretty. If we need to talk about that, we can. If you end up using, you know, if we're taking the test online at home again, and you end up using something like Desmos, actually, I don't know how it does it, so let me see. There's a keyboard that pops up, and we have functions, and we have miscellaneous, and there's your integral. So there we go. So we can do an integral on Desmos from 1 to 4, and we'll just have to put our function right here. But I want to do a function from 1 to 4 of the absolute value of the velocity. I need to put the absolute value function, and that's actually really easy to find right here on the main keyboard. On the graphing calculator, the absolute value is a little bit more hidden. It's under the math menu, but it's under number. And now if I put in x squared minus x minus 6 dx, it's essentially going to do what this is doing as well. Because check this out. If we do the opposite of the integral, and I break this into from 1 to 3, and I just put this in with no absolute value. So when I start doing stuff like this, I'm like, man, I hope I don't screw it up. Okay, so I did that part. And then if I take that and I add that to, now I'm going to do 3 to 4 part of this guy. But if you have the calculator, you don't have to know that you need to split it up and think about it in pieces, because your calculator will deal with that for you. So if you've got a calculator, don't worry about when it becomes positive or negative. You just give it the, let me scroll back up. If you just tell it to do the integral of the absolute value, it'll handle that for you. I just wanted to show you that if we did do it in pieces, like I had suggested, we do get the exact same answer. So the answer for number C, or letter C, 10.16, and AP Calculus is 3 decimal places. You can round or you can truncate. Okay, so at this point, after you watch this a couple times and see what you can do, I would say do problem 3. You can feel free to use your calculator on part B, but you might also just sort of think about where you would split it. Okay. Go ahead and do number 5. Number 5 is 100% calculator. Problem 6 is a good one to do, as well as 7 and 8. Okay. So if you watch the video and you try working through those 4 problems, that's going to put you in a good position for Wednesday's class. Okay, guys. Thanks a lot. Hope you're having a great weekend.